Welcome to Physics 371 Online. We're now going to get into some pretty heavy lifting in our attempt to solve Laplace's equation in a more formal way. We've learned how to use the image method for certain kinds of problems, and when we can use it, it's really useful because it gives us a way of solving for the electric potential really quickly. But some problems don't allow us to do that, and separation of variables is the method of choice that you've probably seen in classes before when we want to solve a partial differential equation, like Poisson's or Laplace's equation. Basically what we're going to do is make a full-fledged frontal assault on Laplace's equation and try to solve it directly. No tricks. Here's the strategy. Given boundary conditions where either the potential or its normal derivative are given on all boundaries of a region of space, we're going to look for solutions that are products of functions, each of which only depends on one coordinate. So even though we might have a 2- or 3-dimensional region of space, so the potential is a function of those variables, we're going to assume solutions that are products of functions, each of which is only of one coordinate. The payoff is, if that works, then when we substitute that solution into the differential equation, Laplace's equation, we'll replace a partial differential equation that has 2 or 3 variables by 2 or 3 ordinary differential equations. And ordinary differential equations are much easier to solve than partial differential equations. So with that as an overview, it's best to work out an example, and I'm going to follow through the example that Griffiths uses in the textbook because it's a very good one. Realize that this method of separation of variables does not give a general solution that will work for all cases. You have to basically treat each case separately because the geometry and the boundary conditions will be different. Here's the example. 2 infinite grounded metal plates are a distance a apart parallel to the xz plane as shown in the sketch. There's no charge between the plates. The left edge of this cavity, which I haven't really been able to show very well on my sketch, but we assume that in the YZ plane there's a left-hand side, and on that left-hand side there's a potential which is a function of y, and we'll call it V0 of y. And our goal is to find the electric potential in between the plates. So the plates are grounded, which means V equals 0, and we want to find V in this slot. I believe Griffiths calls this the infinite slot problem. So what you can see right away is if these plates are infinite along the z direction, then the solution will be independent of the z coordinate. No matter what coordinate of z we look at, the electric potential will have the same value as every other value of z. So it's really only a 2-dimensional problem. So we only have partial derivatives of v with respect to x and y to worry about. The boundary conditions that are important for us to specify are that v is equal to 0 on the top and the bottom plate at y equals 0 and a. V has this function of y dependence on the left-hand side, which is at x equal to 0. And of course, as you go off to infinity along the x direction, v has to go to 0. And so these will help us determine what the specific solution to Laplace's equation is for this case. Since the boundary conditions throughout the entire region are specified, then there's a unique solution. One and only one solution. So let's find it. We assume a separable solution. Separable meaning that the general solution v of x and y is actually a product of a function of x and a function of y. And the question I want you to think about for a second is, why might we expect this? The reason is that if we have boundary conditions, if we go back to the sketch for a minute, that are of this sort, where you have v equals 0 on a conductor for all values of x and z. So there's that particular y value where no matter what the x value is, v goes to 0. The only way that I can think of for that to work for all values of x at a particular value of y is if this function of y goes to 0 at that point. so that no matter the function of x, no matter the value of x, the function of y kills it off. And so that's my hand-waving justification for using separable solutions. Of course, the proof is in the pudding, so let's substitute and see what happens. We substitute into Laplace's equation, and right away you can see that when you take the partial derivatives, you really end up with just ordinary derivatives, because these functions are only a function of one variable. A capital Y is, and capital X are the symbols for the functions themselves. Little x and little y are the variables. So we get this equation, and then in order to separate it, in order to get all the y terms on one side and the x-dependent terms on the other side, we divide through by the product xy. And as we do that, the first term on the left becomes 1 over x d squared x dx squared. The second term becomes 1 over y d squared y dy squared. It's equal to 0. And what we can see right away is that the first term on the left-hand side is strictly a function of x. The second term is solely a function of y. So we'll call these f of x and g of y. And if you think about it, when you have two different functions of two different variables, and you add them together, and you always get 0, no matter the value of x and y, the only way that can happen is if each of the two functions is really a constant. That's the only way that that can happen. And if that's true, then we can write down that the first term, this f of x term, is just equal to a constant c1, and then the g of y term, the second term on the left-hand side, is equal to a constant, so that if the two terms added together give 0, this constant over here has to be negative c1, so that they add together to give 0. The solutions to these two equations, which look identical apart from the minus sign, they depend on the sign of the constant. All right, so let's just look at the x-dependent term. So if we solve for the derivative, we have the second derivative of x with respect to x squared is the constant c1 times the function x. Now, if c1 is positive, then this means you have a function whose derivative, whose second derivative, gives you back a positive constant times the function you started with. And the only functions that behave that way are exponential functions, e to the kx or e to the minus kx. And so in general, we're going to add the two together and know that the solution could be a linear combination of those. A and b in this expression are constants. And let's just remember that the k here, if we were to plug this into the equation there, k squared would be the same as c1. All right, now the opposite case, what if c1 is negative? Well, then you have a differential equation that says the second derivative of the function is equal to a negative constant times the function you started with, and we know that that's characteristic of sines and cosines. So if c1 is negative, then your solution to this differential equation is a linear combination of sine and cosine terms. So now the question is, in our particular problem, which one is it? How do we know the sign of c1, whether it's positive or negative? The way we do it, and this is what makes each problem different from every other problem, because generally speaking they have different boundary conditions. The way we do it is to apply the boundary conditions and see which solution can match them. So, we know for the infinite slot problem that we've just been considering that the potential goes to 0 as x goes to infinity. So if we look back for a second and look at the two possibilities, which one of those can go to 0 as x goes to infinity? And it's pretty obvious that sine and cosines do not do that. They oscillate back and forth between 1 and negative 1. So no matter what the value of x is, as x gets larger and larger, this does not tend towards 0. Neither one of these terms do. However, the exponential terms do. If x is large, the term with the b in it tails off towards 0. The first term grows, and so that won't work for us, but the second term has just the right characteristics. So, we can say that only the decaying exponential term will satisfy this boundary condition, and that means c1 must be greater than 0 because the solution we need is x equals b e to the minus kx. Evidently the a term was equal to 0 because that growing exponential would not satisfy the boundary condition as x goes to infinity. So, as a result of knowing c1 is greater than 0, now we know that the y equation is d squared y dy squared is minus c1y. And so the y functions must be the sine and cosine functions. And so we'll write those. I'll change the constants from a and b to c and d just to distinguish them from the b that we already have here. So we know that that's the general solution for the y equation. And now, in order to find what c and d are, we're going to apply the other boundary conditions, the ones that have to do with the plates on the top and the bottom. So for y equal to 0, the potential is 0, so we're going to take y equals 0 and plug it into the y solution here. Y of 0 becomes c sine of 0 plus d cosine of 0, and the sine term drops out, leaving behind cosine of 0, which is 1, or d, and yet we know the potential has to be 0 at this value of y. The only way that can happen, because the x function is not influenced by the value of y, so the only way that the potential can go to 0 is if d is equal to 0. So that narrows down the possibilities, and therefore the y of y function is just a constant times the sine of k times y. And that means we can take the two functions that we've now determined to be the solutions that match the boundary conditions in our problem and write them like this. ce to the minus kx, that was the function x of x, times sine ky, y of y. And they each had a constant in front of them, but I've just lumped them all into one constant that I'll call c. All right, so we're making progress, but there's still this undetermined constant c, and we don't exactly know what k is either. So how are we going to proceed from here? Well, we've applied the boundary condition on v for the bottom plate. Now what about the top plate? We know that when y equals a at the top plate, that's a grounded conductor, so that v is equal to 0. So we just plug in y equals a into this expression here, set it equal to 0, and see what we get. So v of x and a, just plugging in y equal to a, c e to the minus kx sine of ka equals 0. And of course, c can't be 0, otherwise we would have a trivial solution. The exponential term will not be 0, so the only term that can be 0 is the sine term. So sine of ka must be 0, and if you think about it, that works if ka is equal to pi, or 2 pi, or 3 pi, some integer multiple of pi. We know that k has to be a positive value. We've been assuming that, and k equals 0 would be kind of a trivial solution also. And so as a result, we can say the values of k that make this equation true, that match this boundary condition, are integer multiples of pi over a. Because if you plug those in, you'll see that they will always give a sine of ka equal to 0. N is just the integer, positive integer. All right, so we've made a great deal of progress thus far gathering everything together that we've learned about this problem. We know that the solutions look like this. They're a constant times a decaying exponential times a sine function. And what I've done here is I've plugged in now the results for k that the application of our last boundary condition found us. So we've made a lot of progress, but there's still one more boundary condition, and we have to match the boundary condition that was on the left-hand side of the problem at x equal to 0. And we said on that surface the potential was equal to some function of y. And it could be a sine function, could be something more complicated, but we'll just leave it generically as v0 of y for right now. So we have to match that. We've got to plug in x equal to 0 and set the expression equal to this function v0 of y. And that's easy to do, but it also raises an interesting question. How is it that when I plug in x equals 0 that I can somehow match this arbitrary boundary condition? Because if I look at the equation at the top, if I plug in x equals 0, the exponential term becomes just 1, and so I have a constant times a sine function. How is this going to match the boundary condition v0 of y, unless I get fantastically lucky and v0 of y just happens to be a sine function. However, and here's something important to remember, this solution depends on the value of n. And so there are different solutions for different integer values of n, and if I have two or more solutions, when I add them together, their sum is also a solution. So let's make a sum over all the possible values of n and write that down as our most general solution. We know that n has to be a positive integer, so I'm going to label the constant c with a subscript n to remind myself that those constants might be different for different solutions. And now we see the infinite sum of this solution is the most general way of writing down the solution to Laplace's equation. Now we still haven't matched a boundary condition yet. That's what we're going to do next. But we've got the most general form of the solution. So this already fits the three boundary conditions that we've considered, and now we apply the last one. We say if we plug in x equals 0, then this whole sum should give us the function v0 of y, which is the potential at x equal to 0. So plugging in x equals 0 kills the decaying exponential, giving us this. So now we have hope that picking the right values of the constants c sub n and keeping enough terms in this sum will allow us to reproduce the boundary condition. And there's a formal mathematical theorem called Dirichlet's theorem that says that virtually any function, even a function that's got singularities in it, a finite number of them, can be expanded as a linear combination of sine functions. And so this is actually called a Fourier series, named after the French mathematician Joseph Fourier. So the remaining task we have is to somehow find the c sub n values, the constants, for each of these terms in the sum that will allow us to match the boundary condition. And it's not so obvious how that's done, but there is a way to do it formally. And this is a great trick. This is the only part of the solution that really is a trick, but it exploits the orthogonality of sine functions. So here's our final remaining boundary condition that we apply. And the strategy here is multiply both sides of the equation by this term, which is sine of n prime pi y over a. And then, after multiplying both sides by that, integrate over one cycle of the sine function from y equals 0 to a. Okay, so here's what that looks like. We multiply both sides by this sine of n prime term. So that's right here, and that's right here. And then we integrate both sides from y equals 0 to a. And that means we put a dy on the outside of each side of the equation. All right, so on the left-hand side, we're integrating a sum. And we can simplify this because the integral of a sum is the same as the sum of the integrals of that quantity. And so we interchange the order of those things and pull the c sub n outside the integral because the c sub n is a constant, doesn't depend on y. And now we see something very interesting. When you multiply two different sine functions together and then integrate over one cycle, you find out that you'll always get 0 unless the two functions are the same, unless the arguments are the same. And so if n and n prime are not the same, you get 0 for this integral. If they are the same, you get a simple value, which is just a over 2 in this case. So we have an infinite sum, but it turns out that the only term in that sum that is non-zero is when n and n prime are the same. So everything else gets canceled out. So that means of the whole left-hand side, the only thing that remains is c sub n prime times a over 2. And if I solve then for the c sub n, or n prime, I just get 2 over a times the integral that's on the right-hand side. That's easy to see if you just replace this integral with a over 2 and drop the summation, because there's only one term that remains. And so this equation in the red box tells me what the values of c sub n are that will satisfy the boundary condition. If I just plug in the n value into the integral and evaluate it, I'll get the c value, the constant, for that particular term in the infinite series. So along with the solution, which we already had written down, this expression for the coefficients tells us which values of the coefficients are needed to match the final boundary condition. So if I know the boundary condition v0 of y, then I can just work one term at a time, n equals 1, 2, 3, and so on, and that will generate these individual constants that are needed in the solution. And we'll work out an example and show how this can be applied in class.